All right, so Jeff Hauser with Upper
Midwest Environmental
Science Center is going to talk to us today about long-term resource monitoring, so take it away.
There will be an acronym quiz at the end.
Yep.
All right, thank you for the opportunity to talk this morning, or I guess it's now this afternoon. I'm talking to my computer screen in an office by myself, so hopefully this won't come across as too weird. I haven't quite done this style of presentation in a while. So what I'm going to do this morning is try to just give you a broad overview of LTRM. I want to start out with a little bit of a history of why it came into existence, but that will be very short. I want to talk some about what it does and how it's structured, but I want to emphasize sort of the ways in which LTRM, some of the connections that I see between monitoring research and habitat rehabilitation, and so some examples of those connections. So I wanted to just briefly go back in time to the early 80s and talk about the situation that led to the creation of LTRM. In 1982, there was a very large document of several volumes, many volumes, put together by the Upper Mississippi River Basin Commission. This was the comprehensive master plan for the management of the Upper Mississippi River system. There was one of those volumes, which was several hundred pages, was Technical Report F. And this was described in great detail, not only the need for long-term broad-scale monitoring, but exactly what it should measure. That document was basically the blueprint for what would become LTRM. LTRM was not nearly as large as that document was, because they were thinking really big when they did that. But in any case, there was sort of a long political and administrative and legislative trail from that document to LTRM, and I'm not going to talk about that at all. But the essence of the need for long-term monitoring that was described in that report and subsequent discussions was this. The Upper Mississippi River system it's a complex system. It's both an ecosystem and a navigation system that's valued. It faces complex challenges because of the multiple uses it supports. There are many agencies and organizations whose mission includes some aspect of management and restoration of the river, but at the time there was an acute lack of information about the river and inadequate communication among agencies. So one of the needs that was identified for successfully restoring the Upper Miss was a large-scale natural resource monitoring program, and that is the need that LTRM was created to fill. So where we are now with LTRM is it's an effort that has several objectives, but an important one is to support restoration and management of the Upper Miss with science. The broader UMRR has articulated a specific vision, which you can see on the slide there. And so within the UMRR, as you all, I think, probably know by now, we have two major elements. We have the element related to habitat rehabilitation and the one related to the monitoring. And to effectively and efficiently rehabilitate habitat in the Upper Miss, there are certain questions that need to be answered, as, again, I'm sure most of you are pretty aware of. And those questions are things like which habitats, where, how, and then assessing how we did. LTRM, in collaboration with HREP, has just made a pretty substantial contribution to the information needed to address, especially point A and B there. This is the Habitat Needs Assessment that Nate and Kat McCain and Sarah Schmucker provided a webinar on a week or two ago. So I'm not going to get into too many details about that, but that's one example of how LTRM is supporting these questions. But there's broader questions that need to be addressed too in the context of thinking about the restoration of the river. And these are things like, what is the current condition of the river? How's it changing over time? How does the river function? And how do drivers of that function that restoration actions can alter affect the river? So how can we expect various restoration actions to affect the river as we move forward? So those are sort of questions that I think are kind of specific to each of those efforts. And to sort of now just focus mostly on the LTRM aspect of things, I think there are three fundamental things that LTRM contributes to this broader effort. One of them is an enormous collection of data from which we've been able to learn a great deal about how the river functions and how we might expect it to respond to management actions. The second thing is an extensive network of infrastructure, expertise, and collaboration. So you'll see in the figure to the right there the 6 study pools that LTRM operates within: Pool 4 near Lake City, Minnesota; Pool 8 near La Crosse, Wisconsin; Pool 13 near Bellevue, Iowa; Pool 26, which is at the confluence of the Upper Miss and the Illinois River; the Open River Reach, which is both downstream of the last lock and dam on the river; and then the LaGrange Reach of the Illinois River. And so one of the things I'll mention a couple places today is some ways in which that infrastructure and expertise can be brought to bear on a variety of topics beyond sort of the standard monitoring. And so the third thing I think that LTRM brings is just a broad, improved understanding of the river. And again, I'll provide some examples of that. But to circle back to the data, there are 2 kinds of data, broadly speaking, and I'm going to talk a little bit about each of them this morning. One of them is data at the study reach scale. So this is much more high-resolution biological and ecological data collected using standard study design and methods over space and time. The other is systemic data. This is the land cover data and the Topobathy, both of which I'll talk about a bit more here in a minute. Importantly, all this data is centrally stored. It's publicly available in a variety of raw, summarized, and graphical formats, and that's something else I will show you some examples of here shortly. So I want to spend a few slides just showing you some examples of the LTRM resources that are available online. What you're looking at here is the main web page at the UMESC website. You can get to this directly from the UMRR core website, or you can simply Google it, or you can use the web address that's at the top of the page there. And this is sort of your portal to all things LTRM. And can you guys see the little, I guess it's a check mark. I guess that works as a pointer. So on this page, it's a little bit perhaps dated in its appearance, but it contains the critical information. So we've got links to some basic programmatic stuff, links to each of the long-term monitoring components, so the fish, the aquatic veg, the water quality. There was once a macroinvertebrate component. You can get to that data, but it's not collected any longer. The land cover data, the bathymetry and floodplain elevation data, all this stuff is a click away. There's also contact information for everybody and a link to all the a listing of all the reports and publications that have come out. So a lot of information here. And I want to talk a little bit about some of that information. So I'm going to start with some of the systemic data because I think, given its systemic nature, it is perhaps of the broadest current interest, and then I'll get into some of the more detailed biological and ecological information. So the first of those systemic data sets is what is now called Topobathy. This is the combination of the recently collected LiDAR data as well as bathymetry data that's been collected at various points in time. So the bathymetry data has been merged with the LiDAR data, so we have one seamless coverage of the floodplain and the elevation of the bottom of the river for use in whatever capacity folks are interested in using it in. This is obviously the template on which everything happens on the river and is sort of a fundamental piece of information for understanding the river and planning and thinking about restoration projects. This is just the web page from which you would access that information, the Topobathy link, bathymetry, and the LiDAR. So this is the bathymetry and the LiDAR separately. This is the two merged together. If you're interested in this and need help making sense of what happens when you click on these links and move beyond there, Jim Regala here at UMESC is our resident expert on this. He would be able to get you started. There are some other folks in-house that could probably help you as well, but he would be a good starting point. If you don't know his contact information, you can get it for me, and I have some of that listed at the end of the presentation. So the other systemic data set then is the land cover data. And and this is data that is also collected systemically using aerial photos, which are then digitally interpreted into GIS layers that are also available on our website. And we have some historical data from the 1890s, and then we have the aerial photo derived data sets from 1975, 1989, 2000, 2010/11, and then we're going to be collecting it again in 2020. And this image over here is just an example of one kind of output from that data set. And again, the raw GIS data is available online if you're familiar with how to use that. But if you're not, and you just want to get an idea of what this sort of thing looks like, we have a land cover viewer. This is something Jason Rohweder put together that is accessible at this link here. And this is just something that opens in your browser. You navigate around on the page, very similar to like you might do in Google Earth. You can zoom in or zoom out, move up and down the river, specify the coverage you'd like to see projected onto the screen. When you do that, you get, you can, once you get the image up there, you can get your legend, so you know what you're looking at. And this is just Lower Pool 13, and you can see, and I believe this was from 2010, 2011. You can see the blue is the SAV beds, and then the various vegetation and habitat type areas over here. So that's an easy way to access the land cover data if you just want to visually assess what it looks like. Again, if you want to actually pull it into one of the ARC environments or something and work in a more analytical capacity, the raw data files needed for that are available on the web page.
Hey, Jeff, this is Karen.
Yeah.
The land cover classes, we have a document that describes what's included on the land cover classes shown on your slide. Is that, where is the easiest place to find that? That's an important piece of using this data.
I would guess that if you went to the land cover link here, you would find it.
Okay, thank you.
If you can't, call me, and I'll figure out exactly where it is. Okay, excuse me. So that's just a brief overview of two of the main systemic data sets, and I want to spend a little bit of time on the more detailed biological and ecological data that's collected every year through these 6 field stations. Each of these field stations is staffed by state agency folks from the respective states. So Minnesota DNR, Wisconsin DNR, Iowa DNR, Illinois Natural History Survey, and Missouri Department of Conservation are the folks who are at these stations, who are out in the field collecting the data, and then subsequently they, as well as folks here at UMESC, do a lot of analytical work on that data to extract some knowledge from the data sets. These six study reaches span. I like to describe them as spanning informative gradients of environmental conditions. So, there's obviously a longitudinal gradient. Across that longitudinal gradient, there's a big change in discharge from Pool 4 through the open river. You can see this across the 4 seasons. So the basic conditions in those pools are quite different. The physical structure of those pools is different. This is just showing the relative abundance of various habitat type areas, so main channel, side channel, backwaters, impounded areas, Lake Pepin and Pool 4. So you can see, again, a lot of contrasted conditions in these study reaches, and there's also biological contrasts in terms of whether or not there's vegetation, how turbid the water is, whether or not there's abundant Asian carp. And so because we have data sets that span these various gradients, we're able to assess how some of those things can impact other things we care about in those areas, and use those associations to gain some knowledge about the river more generally. So not just in these 6 study reaches, but more generally how the river functions, and that knowledge, I think, is broadly applicable, and I'll hopefully give you some examples of that as we move through some more slides here. In addition to these differences among the pools, there's informative gradients within the pools. So The sampling for each of these components, the fish, the vegetation, and the water quality, follows a stratified random sampling design. And that is basically set up so that the sampling points are distributed across all of the kinds of conditions that are existing in each of these pools. This is an example of pool 8 showing the various strata in the different colors, so the impounded, backwater contiguous, side channels, main channels are in the light blue. And if you think about how those differ, then this table over here gives you some ideas of the contrast across those different stratum in terms of depth and current and sediment types. You could also think about things like the abundance of vegetation and how turbid the water is. Another illustration of those contrasts is shown down here. So as discharge increases, and this is data from pool 8, how velocity responds to that depends on which of those strata you're in. And so again, as for the differences among pools, by making comparisons across these contrasting areas, we can learn about how the river functions and what that means for what we can expect to happen as we alter aspects of those different kinds of areas. So I guess that wraps up a really brief overview of the basic structure of the monitoring. I have sort of intentionally not gone into a lot of details of exactly how often and such. The substantial details of the sampling design and how often data is collected where, because I think that gets kind of tedious in this format. If you go to the web page and you click on any of the component web page links, each of those components has a procedures manual and substantial documentation of its design and how frequently what data is collected using what gear. And so I would just point you in that direction if you are interested in more information on those details. So again, if you want that information, we have links to the fish page, the aquatic veg page, the water quality page, information on land cover, bathymetry and elevation, and so forth. I do want to show you, so at each of those component pages, you can download the raw data. I'm not going to demonstrate that. Again, that's pretty self-explanatory from the various home pages, but I did want to show you some of the graphical information that's available online, summarizing that data if you're not wanting to download and analyze data, but just get a general idea of what's happening on the river. For example, this is an example from the water quality web browser. If you go to the graphical data browser on the water quality homepage, you'll go to a page that has this header here where you have to make a few decisions. You have to say how you want to compare the data by. So in this case, I chose strata, so it's showing data from main channel, side channel, backwater, impounded areas. Selected pool 13, selected summer, selected turbidity, and then it shows you the long-term trends in those conditions. And it gives you a thumbnail for each of the there on the left. The main channel one is the one that was hovered over when I took this screen grab, so that's indicated in the red outline, and that's the data you're seeing. And more detail on the right, if you hovered over side channel, you get the side channel data. So down here in this lower panel, I've hovered over the backwater contiguous, and you can see the data from the backwaters in pool 13 through about 2015 there. And so if you look at this, you can see there's been a general decline in turbidity, but there was a few years in the main channel in the mid-2000s where that turbidity got pretty high in the main channel, but you didn't see nearly as much of an increase in the backwaters. And so a likely explanation for that is the return of vegetation in that pool and the effect it's had in the backwaters. And you can sort of gain some insights into that by going to the veg graphical browser, which is shown here. So again, if you either go to this link at the top of the page, or if you go to the LTRM homepage and go to the veg page from there, there will be an obvious link to the graphical vegetation browser. If you say you want to look at surface maps, and you choose a pool, I think in this case I chose pool 13, what you'll get is output that looks like this. You can get this for every year. I've showed 98, which was the first year we collected SRS data, and then some of the years where there was a lot more vegetation. And if you look at some of these large backwaters and impounded areas, you can see by 2008, which was the year where we were seeing that increased turbidity in the main channel, we had a lot of edge in these off-channel areas, and we didn't see that increase in turbidity in those areas. So just by spending a little bit of time exploring the data with the graphical web browsers, you can get some, I think, useful insights into the structure and function of the river and how it's changing over time, and thinking about how that might apply that to priorities or ideas for river restoration. If you're further south where there isn't much vegetation, perhaps your interest is more in something like what's happening with invasive carps. And so you could go to the fish web browser in this case, and I cut off the header row here, but it's the same sort of thing. You'd say what comparison you want to make. In this case, it's a comparison across pools, and what you're interested in, silver carp, which sampling method, day, electrofishing, and you'd get output like this. And again, whichever of these you hover over, you get the output over here, and you can see the trends in silver carp through time. The one caveat to bear in mind is that these thumbnails are not all on the same scale, and so you need to actually look at the detailed plots to understand the relative magnitude of the peaks you're seeing there. So LaGrange has a much higher peak than does Pool 26, which is subsequently higher than the open river, and that doesn't come through very well because these thumbnails were oriented around showing the temporal trends, so you're maximizing the range to emphasize that trend, and for making comparisons across, you have to look at the details. So that's one way the data are available online. Another way the data are available online are through an interface called the Spatial Data Query Tool. And Jason Rohweder did most of the work on this. He also just recently put together a fact sheet that is just a few-page publication that walks through a few examples of how to use this. It's available online. I'm sorry, that font in the DOI link there isn't particularly good, but it's on our webpage. And again, if you can't find it, send me an email. And the way this works is quite different than what I just showed you. So the example he has here is using the water quality graphical browser, and what Jason put together for this example is he made selections about the range of years. He picked sample period 4, which is the winter. He wanted to see all the, he wanted to focus the query to the backwaters, and he wanted any of the depths, so he sort of made the depths beyond anything that would have occurred, so that doesn't filter anything. And then he was looking for dissolved oxygen between 5, well, basically greater than 5, water temperature that was at least 1 degree Celsius, and a maximum water velocity of 1 meter per second. So these things are loosely related to overwintering habitat, mostly just a demonstration of how the filters work. So by putting that query together, the output over here to the right, all those points that are lighted up are sample sites where the conditions that meet the criteria he specified were observed between 93 and 2017. That there, depending on how you tailor your query, you can get an idea of what conditions are like where very quickly through this interface. In that fact sheet that Jason put together, he had a second example that was derived that was from the fish version of this, and in that case, he basically asked for all the sites between 2000 and 2017 where bluegill at least 2.9 inches long were detected through day electrofishing. So in the spatial area shown in this picture, each of those dots represents a place where that happened. And this is near the Phase 2 islands near Stoddard, Wisconsin. So two sort of very spatial graphical ways to look at the LTRM data directly without downloading data sets and doing your own analysis. So that is, I guess, the section of the presentation this morning to give you just a really rapid overview of the kinds of things that are available through the website and that anybody can access, and there's a lot more there, but I think that gives you some ideas of the kind of things that are there. And if any of you are interested in more details on the website and what's available there, and there's a number of us here who'd be happy to spend some time giving you a guided tour of that, and I'd encourage you to be in touch. I'm going to switch a little bit now from the sort of nuts and bolts of what LTRM has available as online resources and such to a little bit of discussion of the ways I think that long-term monitoring and research can support and inform habitat rehabilitation and more broadly, river management. So I think of sort of three kinds of ways that this happens. The first thing that it does is, as I mentioned earlier, it describes the current conditions and the long-term trends within the river. So what are the problems out there right now that we need to be addressing? What changes are of concern that we might want to bear in mind as we think about where restoration projects go and what they're composed of? Also sort of in this category of activities are things that just provide a better understanding of the basic structure, function, health, and resilience of the river. In this second category of information is providing just basic information about the river to those restoration and management efforts. So we have the existing data I just showed you, the expertise here at UMESC and at this and distributed across the field stations. There's a variety of ways that data have been incorporated into models that could be that provide predictions about how the drivers that HREPs may change can affect the ecology and biology of the system. And this information also provides the context that's required for effective shorter-term, smaller-scale studies of the effects of HREPs. And what I'm getting at here is, you know, if you look at the data for very long, it's really clear that there's a lot of variability from year to year in what the river looks like and what the fundamental characteristics of it are. And if you are doing some focused monitoring oriented around a restoration project and you're comparing across 2 or 3 years, it is much easier to make sense out of that shorter period of data when you have you understand how the conditions in those few years fit into the broader context of variability over the last 5, 10, or 20 years. And that's something I'd be happy to talk about more with folks in another setting if you're interested in that. And then there's been a few occasions where we've been able to directly study the effects of HREPs. The islands in Pool 8 were one example, and I'll briefly mention some examples of that. I'll show some of the results of that later in the presentation. There is going to be an opportunity in Pool 13 to do some of that as well, since that there's a project getting started in that pool, and that is one of the study reaches. So what do we know about the river condition? Just a brief sort of story here. As most folks know, if you look in Pool 8, the Upper Impounded reach, there has been a substantial recovery in vegetation. This is what it looks like. This graph is what it looks like using the just derived from the stratified random vegetation sampling. This figure shows what it looks like spatially. And associated with that change in vegetation has been a long-term increase in water clarity or decline in suspended solids, and this has been seen in Pools 4 and Pool 8, and to a little bit lesser extent Pool 13. But if you go to Pool 26 and you look at the long-term trends in suspended solids, there hasn't been any downward trend. There hasn't been a recovery of vegetation. So because our data collection spans this range of conditions, we're able to observe what's happening in areas where certain changes are happening and in areas where those changes are not happening, and that provides us some initial information about why we may be seeing changes in some places and not elsewhere. And there's actually a couple research projects going on right now to directly address some of that, and I will talk about that a little bit at the Science in Support of Restoration presentation next week. So another example of sort of synthesizing this data to inform management and restoration is work Yao Yin did a number of years ago, where he pulled together a variety of input data, so water velocity, overall pool bathymetry, wind fetch, so this is how much open water area there is, also light extinction coefficients, how turbid the water is, and river stage, to make predictions about where vegetation would and would not occur. and how that distribution might change if any of those drivers were changed. And one detailed aspect of that is just sort of better describing the various elevations, bottom elevations at which various vegetation species were most likely to occur. So indicating the importance of bathymetric diversity, and also if you're interested in particular kinds of vegetation, thinking about what sort of elevations or water depths those vegetation thrive at. Some analogous work was done with the fisheries data. This is work Brian Ickes and colleagues did with the second generation AHAG models, where they constructed spatially explicit models for 28 fish species using LTRM fish and environmental data. And so the output, an example of that output is seen over here. So this is a map for predicted probability of occurrence for black crappie in pool 8. The different colors represent the different probabilities. And, you know, some of the value of this sort of information is it tells you where fish currently are found and what their habitat preferences are observed to be. And, you know, where fish currently are seems as though it would be useful information for thinking about siting of future projects. And the habitat preferences of the various fish species seems to, like, it could provide important information for the design of those projects. So it seems like there's some pretty direct connections between this work and thinking about restoration projects. Some other work that's come out of LTRM directly related to restoration project efforts is work that Jason Rohweder and some of his colleagues did, trying to assess how, or coming up with a tool that would assess the way in which different island configurations would affect wind fetch and therefore the probability of sediment resuspension. You know, some of these projects are established in the wide open impounded areas of navigation pools in order to cut down on the overall wind exposure or wind fetch and reduce sediment resuspension. And so this was a tool that you could specify different configurations of islands and look at what the implications are for their effects. I mentioned earlier that we've also, in a few cases, been able to use LTRM data to directly assess impacts of projects. This photo here is for Pool 8 islands. And because we collect veg data here as part of LTRM, it was possible to do some assessments. And the first study that did this was work by Heidi Langer and Brian Gray and Jeff Janvrin. And the way they approach this map over here shows the schematic of where the islands are. I believe when this study was done, only the purple and green ones had been completed. And so they divided up the area into reference areas that they didn't expect to be affected by the islands and island areas that they did expect to be affected, and they looked at the differences in the data between those two places. And that's what's shown here. So the reference is gray. The island areas are white, and this is 1998 and 2000, and you can see the contrast in vegetation between those areas. Subsequent to the completion of the rest of the islands in that pool, an additional study was done by Dan Drake and folks just a few years ago, looking at both the impacts in areas directly adjacent to the islands and then broader, what they called indirect impacts. And what they found in that study was that by the time that third set of islands was completed, the vegetation had already recovered to such an extent that the response in the immediate area of the islands wasn't possible to detect, but the areas that were identified as places where indirect effects of vegetation were expected did show evidence of a response to the completion of those islands. So those were both studies that looked at the just basic distribution of vegetation. Is it there or not? Recently, Alicia Carhart and Nate Dieger finished up a study that was looking at how the species change over time, in addition to the percent frequency of occurrence. So what this is showing here is a couple maps of Pool 8. Percent frequency of occurrence in 1998. The blue is low frequency of occurrence, yellow is moderate, and red is high. You can see most of the veg is in these backwater areas by 2016. So this next map shows the change between 98 in 2016, and red is a lot of change. Yellow is sort of small declines or increases, and blue is a major decline. And you can see that much of that change increase occurred in the impounded areas. But when they looked at, what was interesting was when they looked at the species composition, they looked at two kind of contrasting communities, one dominated by wild celery and water stargrass, another one dominated by coontail and Canadian waterweed. And this shows that the distribution of, or the areas that tended to be dominated by wild celery, in I think that was 98. I'm realizing I don't have that on the screen here. And then as they looked at the change over the duration of the sampling, the blue indicates a transition from wild celery to coontail and Canadian waterweed. Yellow indicates not much change in composition, and I forget what red indicates. But the main point here is in these areas that were created to be backwater-like by the islands, the vegetation community has become more backwater-like and less like it is in the flowing water areas of the impounded zone. So really digging into sort of species-specific, or at least, taxonomic changes in the vegetation resulting from island construction. So that's just a couple examples of efforts LTRM has been involved in that tie directly to topics related to restoration and management. I want to mention two other things, and then I'll be done. So there's not a whole lot left here. One of them I just want to mention in case anybody was not able to attend the seminar that Nate Dieger and Kat McCain and Sarah Schmucker gave. I can't remember exactly when it was, a week or two ago, maybe 2 weeks ago. If you didn't get a chance to see that, I'd highly recommend you access the slides. I believe they're available online. I think eventually the whole webinar will be online. Karen Haggerty can update you on that. But the basic thing here was there were two parts of this habitat needs assessment effort. One was sort of quantitatively assessing the condition of the river, or the current condition of the river using a variety of systemic data sets. And so this was essentially an overview of what we know about the river at a systemic scale. And I will say that in addition to the basic indicators that were put together, that I'm sure, I wasn't able to see that webinar, but I'm sure Nate and company described quite well in the webinar, the report itself has a lot of useful information about other studies and what we know about various aspects of the river related to those indicators. And I would encourage you to take a look at it in some detail if you want to have a better idea of what we know about the river's structure and function at the systemic scale. The second part of that effort was the actual habitat needs assessment, and this was sort of where what we know meets what we want. And this was essentially the result. This was produced by each of the river teams working with the indicators report that Nate and company put together, and using that and comparing what was described in that to their desired conditions in the areas of the river they were responsible for, and indicating the extent to which the current conditions were acceptable or not acceptable. That wasn't the scale they used, but that was the gist of it. And again, so that's all I'm going to say about those two, except that I think it's a really great example of taking a very sort of quantitative approach initially and describing things in great detail using a remarkable data set, and then thinking very carefully about what that means for what our priorities are going forward. And one nice thing about the Habitat Needs Assessment Report itself is I think it does capture a lot of the discussion that went on at those river teams. And again, I guess it's just a plug for both of those. If you have a chance to look them over before the workshop next week, I think that would be a productive use of time. The final thing I want to mention just briefly is something that has been going on for a while now, and we've made a lot of progress on, which is the overall resilience assessment. This is work that Kristen Boschke and myself and a few other people have been doing in coordination with a larger group of folks making up a resilience working group. And again, I don't want to spend a lot of time on this because we don't have a lot of time today, but I want to mention that it was out there and a couple products that you could take a look at if you're interested. The first one is this first publication we put together on this was something called the System Description Paper. And to step back for just a minute, the overall objective of this resilience assessment was to improve our understanding of the current resilience of the river and the potential for management restoration actions to affect the resilience of the river. And we also were trying to identify some indicators of resilience in areas of uncertainty where additional study is needed to better understand the resilience and how we could manage to improve it. And so this first paper, the system description, was basically intended to develop a more or less agreed upon simplification of the river that clearly identified the fundamental characteristics of the system in the context of resilience and its management. And so we put together, as part of a lot of discussions with a lot of people that started with a workshop in January of 2016, a number of conceptual models describing the river. The broader overarching conceptual model is the one you see here, which conceives of the river as sort of having three interacting sub-areas: lodic channels, so lodic means flowing water; lentic areas, lentic means still water; and then the floodplains, and thinks about the various ways in which those interact. And then for each of those subsystems, there was a conceptual model that was based on starting out with what the valued uses and ecosystem services that were derived from that part of the river were, and what the major ecological resources that were needed to support those uses, and then what the major controlling variables, this column over here on the right in the boxes, that affect those major resources were. And part of the idea with this was to use these conceptual models as a way to synthesize all the things that we've learned over the last 20 years about the connection between these driving variables and these response variables, and the work that's happened with an LTRM, and to identify sort of the most important things to focus on moving forward. The second major product that's come out of this effort is was a development of indicators of general resilience, and a subset of these ended up in the indicators report for the habitat needs assessment. So this was something that went on prior to that indicators report to provide some input to it. And the basic idea here was to work with three principles of general resilience. These are things that are largely understood to affect the ability of the river to cope to disturbance and surprises and changes. And those three principles are maintaining the diversity and redundancy of the system, maintaining its connectivity, and managing various controlling variables and feedbacks. And so the indicators that were described in this report are listed here. I'm not going to read them all, in the interest of time. But the summary of that report took each of these indicators. So each of these web plots over here represents one of the geomorphic reaches. Each axis within each of these figures corresponds to one of these indicators. Close to the middle is a low value, close to the edge is a high value, and the idea was the greater the area of color you see, the more positive the indicators of general resilience are for that particular reach. And so it was a way to compress an enormous amount of information into sort of a broad, quick overview of the condition of those reaches. And again, that is a publication I'd be happy to get to if you're interested, or Kristen can set you up with that as well. So just to wrap up, thinking about moving forward from here, I think the intent is to continue to use LTRM data to learn about how the river functions and better anticipate how it will respond to management and rehabilitation actions. And I'm going to talk about this in a lot more detail at the Science and Sport of Restoration section at next week's workshop. I think that we would benefit from better understanding what the largest sources of uncertainty are for the biological and ecological responses to HREPs. So this is a question that I have to many of you at the workshop next week. Those of us who spend a lot of time working on thinking about the LTRM data are very interested in what those biggest sources of uncertainty are in terms of how the river is going to respond to the projects that you're designing and putting in. And also, we are continuing to look for opportunities to learn from the effects of restoration and management actions on the river. These restoration projects are large-scale manipulations of major drivers of the river and provide a lot of opportunities to understand how the biology and ecology of the river responds. And it's something I think we could get better at taking advantage of. There are a few existing examples that Dave Bierman is going to talk about next week I showed you some work in Pool 8 looking at vegetation data. Dave Bierman's and his colleagues at the Pool 13 field station have been working with overwintering studies in Pool 12 associated, so they've been doing a lot of the field work and data collection associated with some HREP work there. The staff at Pool 4 field station, so this was largely Rob Burtis and his colleagues, have been collecting a lot of winter data associated with modifications that were made to the Peterson Lake HREP. That HREP, there were issues with essentially too much connectivity remaining and water velocities being higher than desired, and so there were some additional changes that were going to be made, and Rob was doing some before, during, and after measurements of what happened to water velocity and dissolved oxygen and temperature in response to those changes. And again, those second two on that list are going to get talked about some more next week, but I just wanted to mention them as an examples of the LTRM field station infrastructure and expertise being brought to bear on gaining a better understanding of the effects of restoration projects. So that's what I have. This slide is a little bit of a mess, and some of the font colors, something happened to. But for the most part, if you have questions, and some of the person talking today, I volunteered myself as being the main contact point. So there's an email and a phone number. But there's a lot of folks here and at the Corps that can help with questions. Jenny Sowers, our branch chief. Brian Ickes is our fisheries PI. Kathy Jo Jankowski is the water quality PI. We have all but hired a vegetation PI, and that will be announced soon. Nate DeJager is our landscape ecologist and has done a tremendous amount of work with the land cover data. And Jim Regala has been very involved in the Topobathy work and has some ongoing sedimentation projects. So if you've got questions along those lines, feel free to get in touch with him. You can find all their contact information at that very difficult to see web link above there from the Army Corps. Obviously, I think you probably know, most of you know all those folks, especially Marshall and Karen. We have a group of folks that provide some technical connectivity, I guess, for lack of a better word, between LTRM and HREP. And so this is Dave Potter, Shaytel Henderson, and Kat McCain. So those are also folks that could start pointing you in the right direction if you have questions about anything related to LTRM. And that's what I have for this morning. Thanks for your attention, and I would be happy to take questions now, or you can also come find me next week. I'll be at the workshop all week if you want to talk about any of this in more detail. Thank you.
Thanks a lot, Jeff. We do have a couple questions that were typed into the chat that I will ask you, and then I don't know, you may have gotten some questions directly yourself. So if you do have any, we'll have you ask yourself those. The first question is asking about what parameters have been eliminated from monitoring since the 1980s, and the example they give is chloride being eliminated in the early 2000s, and also asking about what the reasoning was for eliminating those parameters.
Yeah, thanks. That's a good question, and I'm not going to be able to answer it comprehensively. Chloride and a variety of metal ions was eliminated in the early 2000s, basically because we had to make the program smaller, and that was one of the things that was sort of didn't win or didn't come out ahead in the cost-benefit discussion of the value of the information. In retrospect, the chloride data is an unfortunate decision. Having said that, we have a lot of data up to about 2000 with chloride, and there are some ongoing discussions about reinstating at least the chloride data, and if we can gain a few years now, I think that we could make some meaningful comparisons to what it was, a decade or two ago. We have for the water, if the question is primarily about water quality, there is on the website in the water quality page a link that goes to a PDF that is essentially a one-page table that describes all the changes in the sampling, both the number of samples collected and the things being sampled over time. So I would point the person in that direction. And if whoever that is wants to send me an email, I can give you more specific information about the details of that.
And we will give you an opportunity to respond in writing, too. to these questions as well.
Yeah, but it's also the macroinvertebrate component was eliminated also in, I think 2003 was maybe the last year.
Yeah, and so there was also in the early years a bathymetry and sedimentation component that Jim Regala was one of the main leaders of. That was essentially, that went away for a long time, and in the last couple years, as a result of some increased science-supported restoration funds and work, we have returned to some of that and are returning to collecting some of that sedimentation data for at least a number of years now. So yeah, the macroinvertebrate stuff, some of the sedimentation work within the water quality component, I think in terms of the actual parameters measured, the only thing I know of was that suite of metal ions and including chloride. And most of what changed was the other thing that there were a number of fish gears that are no longer used that were used in the early part of the program. So the fish component samples, because different fish and different aquatic areas are most effectively sampled with different means. They use a suite of different sampling gears, different kinds of nets and day electrofishing. They used to use more gears than they use now. Again, as part of that sort of making the program smaller that happened in the early 2000s, some of those gears were dropped and are no longer used.
Thanks a lot, and thanks to Jenny Sauer. She's been popping up some references that are backing you up as well.
Okay, thanks, Jenny.
All right, next question I have is asking about Yin's veg model for Pool 8 and whether it's usable in other pools.
That is a good question that I will have to talk to Jim Regala about a little bit as to how transportable what aspects of that are. I know that a derivative of that I think was used in some work north of here, and I forget where. But
Starved Rock Pool?
Starved Rock Pool, wasn't there also something out of the Minneapolis folks were working on?
I think that was a different model that
okay.
Yao and Derek Ingleson were working on for Northern Sturgeon Lakes up in Pool 3.
So I